So we are going to talk first about diffusion current. Diffusion current happens where you have particles that flow from a high concentration to a low concentration. So basically you get some that migrate and they all even out. And I won't promise that those are exactly evened out, but they're kind of evened out. I think about half of them went over there. Depending on whether you have electrons or holes moving, that will create a current, either one, and the direction of the current depends on what kind of particle is moving. So if you have electrons, they diffuse in the positive x direction, but then the diffusion current goes in that direction also. Hole diffusion current actually is in the negative x direction, so it goes the other way. And, you know, pretty much all you need to remember from that is that there is current that does that, diffuses. And it's part of total current, but we don't generally, we don't usually add them together. They're just both going on at the same time a lot of times. One of the problems with talking about diffusion current is because semiconductors are three-dimensional objects. And carriers diffuse in all directions. If I tried to mathematically talk about three dimensions, it would be too much for your poor little sophomore brains to handle, or even your senior brains. So I'm not going to talk about three dimensions. I'm talking about one, just to keep it at one. I will at the end say, if we did three dimensions, this is what you'd have. So you will know at least where it goes. But I'm really only going to talk about one dimension, and then one could extrapolate it into three if we need it. So usually when we look at carrier density, we represent it graphically. So what we have is we have two graphs. On the left side of each, the vertical axis gives you the concentration of either electrons on the left or holes on the right. And as you have a distance, whatever that may be, from point A to point B, so you assume that the zero distance is right where the two axes meet, and then distance just carries off from there. And according to both of these graphics, the hole concentration and the electron concentration is increasing as that distance increases. So there would be a linear function that described this, basically this gradient. And whatever that linear function might be, that would describe how this concentration worked in really one dimension. So each one of these, if you have a gradient, creates a flux of some sort. And in electrons, the flux is created in one direction. The hole also creates flux in the same direction, but the current is opposite depending on if you're talking about conventional direction or electron direction. So we also notice that the current direction is opposite from the actual movement. That's because electron flow is opposite to conventional current, so that's why that's kind of weird. And both of them create flux in the opposite direction of the gradient, which, again, this is a theoretical thing, not a thing that you need to worry over much about. We'll go through how we would figure out this kind of problem. So the electron diffusion current density, which is, we talked about drift current density, now we'll talk about electron diffusion current density. It's towards the higher concentration, and you can quantify it by taking the charge of the electron and then multiplying by something called the electron diffusion coefficient. That is a constant. You can go look that up. It's on a table. It's actually on the same table as mobility for a reason that I'll explain later. And then we have the derivative of whatever the function is that describes the gradient. So it's not going to be a complicated derivative because it will be a linear equation. So if you have a linear equation, you take the derivative, it's going to be really, really simple. So that makes it not so difficult. For holes, same thing. The only difference is that the diffusion current density from holes is in the same direction as the flux. That's the only real difference. And we use the negative of the electron charge because we're talking about holes and not electrons. So that's the only difference. Nothing complicated. So let's look at an actual example which will hopefully make it make sense. We will see. It might and it might not. So we have an equation, sort of. We have hole concentration that's varying linearly, which is good, from 0 to 0.01 centimeters. And we know the diffusion coefficient for the hole, and we know the diffusion current density, and at x equals 0, we know the concentration of holes. And we want to have the hole concentration 0.01 centimeters away from that. So we know that the diffusion current, and this is the x-dependent diffusion current for holes, is equal to minus E times the diffusion coefficient times the derivative of whatever that equation is. We don't actually have an equation, but we do have a relationship we can use. We know that the number of holes at 0.01 centimeters is going to be what we want to find out, and that's all buried inside that equation somewhere. Minus the number of holes at 0, which we actually do know, divided by the distance, which is going to be the distance really between 0.01 and 0. That will give us basically the change in holes over the change in distance. So rather than taking an equation and taking the derivative, we just took the absolute definition of dp dx and wrote it down. So it's a little bit different. So what this means is the number of holes at 0.01 centimeters, and I'm just doing algebra, but I'm doing it all at once, not in little pieces. So the diffusion current density is going to be multiplied by what was on the bottom of that equation. So we get 0.01 minus 0. So I'm not going to put the minus 0 in there because we all know what that is. And then the negative E dp is going to be on the bottom. And then we'll have to add the amount we had at the beginning. So now it's just a question of put in numbers and get an answer. So the number of holes at 0.01 centimeters is going to be the diffusion current density, which is 20 times 0.01 over minus 1.6 times 10 to the minus 19 times 10. And we add 4 times 10 to the 17. Now, what you will notice is even though we're adding, there is a negative on the left-hand side. So we're actually, what's on the left is going to be subtracted from, not added to, but it just means there's going to be less 0.11 centimeters away than there was when we started with. So this works both ways, which is good. And when we get the answer, we get 2.75 times 10 to the 17 per cubic centimeter. I will tell you that that is not the kind of thing that I would ask you on a test, because you would create so many answers I would have a terrible time grading it, just because it's kind of a pain to do those. So sometimes I put those as homework problems. I don't remember if I did this time or not. But that's really all you got to do with diffusion current. You just have to know kind of the function that describes it, and it will be linear. And then you just basically plug it into whatever you have. Now, the total current density, since we talked about drift current and we talked about diffusion current, the total current density is all of this stuff added together. And that is in one dimension. So that is only in the x direction. If we actually wanted to take this into 3 dimensions, we could. The nice thing about the drift current is the electric field is applied in 1 direction. So we don't have to extrapolate that into 3 because the actual forcing function is just going to force it in 1 direction. But for diffusion, it goes in 3 dimensions. So basically what we end up is we have to use the gradient and partial derivatives of the function that describes the gradient. So the gradient would be given as a function in 3 dimensions, and then we would have to take the partial derivative in each direction and add them together and get the gradient, and then that would give us the value. No, I will not make you do that. Yes?
I was just going to ask, what's the upside down delta mean?
That means gradient of n. That is actually defined as the partial derivative in those 3 dimensions. I don't remember where in the world in math you get to that, but Calc 3, okay, that I don't remember. I minored in math, so I went through all that stuff, but it's all a blur now. But divergence and curl and gradients are really cool when you get to them. They're really neat. We're not going to use them in here. I'm just saying this is what you would have to do to get to this point. Another thing that can happen is that you can have a semiconductor that is non-uniformly doped, and that happens quite frequently. The interesting thing is, let's look at this just for a second, because this is going to happen again later. The Fermi energy, you will notice, is horizontal, and it doesn't change. The conduction, the intrinsic Fermi energy, and the that should be a V, not an F back. Sorry, that's a V. There we go. Those values can change. So the energy level of the conduction and the valence and the intrinsic value can change depending on what the doping concentration is. And they will, depending on what happens. In fact, when we put P material and N material, they'll actually kind of bend when they go through. But the Fermi energy will always be horizontal and will always be the same. So what this means is that at this end, this is like N-type material right here because the Fermi energy is right close to the conduction band. Over here, this is closer to intrinsic when you get there. And if the doping concentration continued, you could actually get to P material. If that happened, if that gradient continued, that would be what happened. So the actual thing that describes this, there is a mathematical way to describe this. This will create an electric field if you have non-uniform gradient. That's pretty much a given. And the way we figure out the value of the electric field is something that might look familiar. Yes, there's where the electric field comes from, because the electrons will kind of diffuse. And what we have is kind of, it's not terrible, but remember that KT over E, that's just that 0.0259 value we always use. And then we would just have to know the donor concentration function, and then we could figure out what the electric field is. So we will look at an example of that. So we have a function that is describing how the doping concentration works. And this is a donor concentration. So what it's saying is that it's at 0, 10 to the 16, and then as it goes, we have to do this function to tell you what the actual value is. So that means that the derivative of this function is just going to be minus 10 to the 19, and actually it would be centimeters to the minus 4th, but I'm not going to worry about that. So the derivative is minus 10 to the 19 because the constant goes away and the x goes away. And then that means the electric field is going to be minus KT over E times 1 over the function times the derivative of the function. So that gives us minus 0.0259 times minus 10 to the 19 over the function, which is 10 to the 16 minus 10 to the 19 times x. And if we go through and actually find that, we get 25.9 minus 0.0259x. And that means if we wanted to say find the electric field at any point, we could find it. The electric field at 0 is just 25.9 volts per centimeter. And then for each value of x, it would gradually decrease and go down because we're subtracting, and we could get the electric field at any point. So it's not very difficult to figure out what that electric field would be, as long as you know the function of the density gradient, which might or might not be easy to find. Doing good so far. One last thing with this lecture, and then I will do the next one. Mobility and diffusion are related. They're not independent. Mobility is how fast something can move. Diffusion is kind of how fast it moves also. And they're actually related. And Einstein was the one who put this together. He was busy with a lot of stuff, and this was one of those things he did, I guess, in his spare time, perhaps. But he determined that at any given temperature, the diffusion coefficient divided by the mobility is a constant. So if we figure out that we're at 300 K, the value of KT over E is 0.0259, and that means that the diffusion coefficient and the mobility have to keep that same ratio. These are typical values at 300 K, and you don't need to go and check if those ratios are correct, because they are. But basically this means if you know the mobility at a particular temperature, you can figure out the diffusion coefficient or vice versa. So I can do one last example with that, and this is a kind of a dumb example because it basically, we can find the diffusion coefficient if we're given the carrier mobility, and that value is just KT over E times the mobility. And since we're at 300 K, that's 0.0259 times 1200, and that gives us 31.1 centimeters square per second. So that is not even worthy of assigning you as a problem because it's super simple.